We use software simulation in all aspects of the design and development. Our primary use of it was to do functional verification of the x86 architecture. Literally billions and billions of cycles were required to verify the architecture and make sure that it performed all the functions as spec'd. Our C++ model was an RTL representation of the design. The implementation teams took this representation and implemented gates. So we had two representations that we had to guarantee were equivalent. As I said earlier, most of our functional verification was done on the C++ model, on the RTL representation. So to guarantee equivalence between the RTL and the gates, we created a special cross-verification environment where we were able to simulate both the RTL and the gates simultaneously, and on a cycle-by-cycle basis compare the output of the C++ with the output of the gates. In using this methodology, we had a need for a very large amount of simulation throughput. And to achieve the simulation throughput, what we did is we used a commercially available batch queuing system or load sharing system that allowed us to distribute the simulations across thousands and thousands of machines or processors in the company. So using this methodology, we were able to run through our whole regression suite in a matter of a couple of days, where the simulations would run on basically all the available CPU cycles in the company, including those on the engineer's desktop.
Well, there are two areas that you need to consider when modeling a microprocessor. The first is how are you going to represent the logic that represents the actual design. That traditionally has been done using hardware description languages like Verilog and VHDL. The other aspect is the simulation environment. This is the part of the model that provides stimulus to the model and checks that the model is actually behaving correctly. K6 design, as you know, is very complex and needs a lot of verification. So the amount of code that goes into that simulation environment is significant. The hardware description languages that I've mentioned are really not very good general-purpose programming languages, and this is the primary reason why we chose to use a general-purpose programming language to represent the entire model, both the logic and the simulation environment. We chose C++ specifically because of its object-oriented nature. That allowed us an elegant way to represent the logic, and also a way of representing the complex models of the expected behavior. Additional benefits of using C++ is it's a compiled language, and as a result of that, the final execution model is quite fast and compact. You need a fast model because you've got to minimize what I call a design loop, the time that it takes to identify a problem, change the design, recompile it, check that you've actually got the design working correctly, and you have to do that many, many times throughout the project. Additional benefit of C++ was that we could use a public domain compiler. This meant that there were no licenses required. So we had at our disposal the computer resources of the entire AMD network, which was well over 1,000 computers. Throughout the design, you find that simulation throughput is always a key limiting factor, and this allowed us to minimize that impact on the design schedule.